All right. Hello, everyone, and welcome to the first seminar of the term. So today we have a speaker who is in Texas. So this talk will be online. And as I think I mentioned in my announcement this morning. Welcome to the first seminar. Sorry, forgot about that. There we go. As I mentioned in my announcement to the seminar this morning, the next two speakers after this will be live in Salisbury Labs 15. So we'll be back to our former schedule. One of them from Alfred University in New York State, the other one from Ambry Batteries here locally. So it'd be great to have some live speakers again.
But they'll still be live streamed on Zoom, correct?
Yes, that's right.
Okay, thanks.
Okay, great. So with that, I will turn it over to Kubra Karagis, who's going to introduce her former PhD advisor. So please go ahead.
Thank you. Hello, everyone. Welcome to today's seminar. It's my pleasure to introduce Professor Raymundo from Texas A&M University. He has a BS in Mechanical and Electrical Engineering from Mexico, and MS in Material Science and Engineering, and PhD from Material Science, both from MIT. After finishing his PhD, he worked as a postdoctoral researcher at Penn State University. He is currently a professor in the Department of Material Science and Engineering at Texas A&M University. Also, he holds colleges appointments with departments of Mechanical Engineering and Industrial Systems Engineering. His area of expertise lies in the field of computational material science, with emphasis in computational thermodynamics and kinetics of materials. He and his group uses several tools, including ab initio methods, classical molecular dynamics, computational thermodynamics, and phase field simulations. And their recent focus is on simulation and data-enabled materials discovery and design in a wide range of contexts, including additive manufacturing. He has over 210 publications, 20 conference proceedings, 120 conference papers, and 100 invited talks. He is the recipient of several awards, including NSF Career Award, TMS Early Career Faculty Fellow, TMS Prima Combi Medal, and ASM Fellow. He has been named as the Texas A&M Presidential Impact Fellow and University System Chancellor Aegis Fellow. He holds the position as Dean's Research Fellow since 2021. He is the associate editor in several journals, including Materials Letters, Integrating Materials and Manufacturing Innovation, the Journal of Phase Equilibrium and Diffusion. He is the chair of the ASM Alloy Phase Diagram Committee and TMS Functional Materials Division, and also a member of the board of directors of TMS. He chaired or co-chaired more than 15 symposia and has been the lead organizer and co-organizer of several international conferences. Today, he will be giving us a talk on towards 3D plus printing of metals and alloys. So before handing it over to Professor Arroyave, already Professor Powell mentioned, but he was my PhD advisor, and I feel lucky to work with him and very happy to have him as our speaker today. Welcome, Professor Powell, Professor Arroyave. Sorry for the excitement. So yeah, I'm gonna stop sharing right now, and it's all yours.
Thank you, Kubra. Thank you, Adam, for the invitation. It's really nice. I mean, I have known Professor Powell since my days at MIT, and it has always been great. We have been interacting with each other, for 20 years now, so we're old. And I'm really glad. I'm kind of sad that I couldn't travel in person. There was a review meeting that was conflicting with the travel, and then that review meeting was canceled, but it was canceled too late to change my travel plans. So it has to be done virtually, but we're all used to virtual seminars now, right? So anyway, so today I'm going to talk about 3D plus printing of metals and alloys. And, I'm going to get started. I understand that this is a materials and manufacturing seminar, if I'm not mistaken. So I think that this topic is especially suitable for this symposium. So this is the outline of my talk. I will give a brief background introduction to additive manufacturing. I'm sure that most of you, if not all, know about it. But to make the presentation complete, I'm going to talk a little bit about additive manufacturing in general, and then I will start with the topic of this talk, which is basically trying to go beyond 3D printing, specifically focus on two types of projects that we're working on. One is called, what is on 4D printing of metallic systems, and the other one is on functionally graded materials design. And then I'm gonna end with some conclusions and future work. I definitely, this is work not done by myself alone, so I need to acknowledge the groups of Professor Ala Elwani, Ibrahim Karaman, and Richard Malak, because this is, what I'm gonna present here is basically the product of a highly interdisciplinary and collaborative effort. So additive manufacturing, as you all know, is a process of building a three-dimensional solid object of an arbitrary shape and complexity from a digital process, right? So you basically design a part in a computer, and then you basically transform that design specification into machine code that instructs the machine, whichever technology you're using, on how to deposit material on a layer-by-layer basis, right? So additive manufacturing is an additive process where materials are deposited on a layer-by-layer basis and is distinguished from subtractive manufacturing that relies on material removal, right? So this is, the distinguishing aspect of additive manufacturing, and it has, become incredibly important in many industries. It started in the 90s, and actually I remember that there were faculty at MIT, like Professor Sima, for example, and even my advisor, Thomas Eager, that were working on additive manufacturing as a rapid prototyping technology back in the 90s. However, in the past decade, particularly, it has, gained increasing industry relevance and has been deployed in a wide range of applications. And of course, it is supposed to be a dominant. It's not going to be the only, manufacturing technique, but in some applications, it may likely be the dominant manufacturing approach in the near future or now, right? And here I'm just taking a picture from Roland Berger's report, where he's actually looking at different types of industries and the manufacturing readiness level scale when it comes to being amenable for additive manufacturing. It turns out that dental applications have all kinds of additive manufacturing technologies. Tooling is important, aerospace, and so on, right? It tends to be that additive manufacturing tends to be more economically feasible and attractive whenever the part that you're making is both geometrically complex, so you cannot manufacture it in any other way, and you're actually printing or making things that have high value, right? So in any industry where you have a high value proposition and the thing that you're trying to manufacture is complex, additive manufacturing may play a role. Now, there are many benefits to additive manufacturing. For example, because you're building materials or components on a layer-by-layer basis, you have considerable freedom in terms of the geometry topology of the part that you're making, right? So it gives freedom to do really optimal design for whatever application you have in mind. Because you are 3D printing complex geometries at a time, you can, consolidate a lot of parts. So there are examples that are already deployed in industry where a part that used to consist of 15, 20 components is turned into a single part through additive manufacturing. And of course, this has a lot of benefit because your inventories become simpler, your supply chain becomes easier to manage. The provenance and verification of your components is easier to handle, and so on. Another advantage is the fact that you can customize your fabrication. After all, you're designing stuff on a, you can, print, components and parts on an individual basis. So that means that you can design components specifically for the application that you have in mind, and you can basically mass customize your fabrication, right? And another advantage of additive manufacturing is that, if you do additive manufacturing, you can actually, significantly save the amount of material that you need to begin with to fabricate a part, right? And this is important because in subtractive manufacturing, we start with a block of material and then we sculpt away, the material to get the shape that we want. Here, we're building the shape from the ground up. Now, the question here is, can 3D printing do more than just allow you to create geometrically complex, consolidated, customized, mass efficient parts, right? And, to take some inspiration, if we look at synthetic materials, they tend to be monolithic, simple, they tend to be primitively hierarchical, and they tend to be extremely limited by the manufacturing process, right? So the stock that you use to then fabricate complex parts has to be very simple in geometry. Composition is uniform, and there's not a lot of freedom in terms of the design that you can use. Natural materials, on the other hand, tend to be very complex, right? You have hierarchical structures, and more importantly, in natural materials, you actually have location specificity. What does that mean? That every location of, a biological structure may actually have a specific, hierarchical arrangements, right? That are tailored for a particular function, right? So every component in a biological material may have different microstructure, they may have different chemical makeup, and that makes them to have different properties that are especially adapted for the particular function that that particular object has to have, right? So for example, in the case of bone, different parts of the bone are going to have different stiffness and different strength and different mechanical properties depending on the loading conditions and the function that that bone has in an animal body, right? So, the current value proposition of additive manufacturing is, based on the fact that you can, build highly customizable and complex shapes that make the design of the component more efficient. And yet, we believe that the underlying 3D printing technologies can be leveraged to achieve much more, right? So the question here is, how can we leverage the fact that we can build materials on a layer by layer, and in some cases on a voxel by voxel basis, and leverage this flexibility that we have by fabricating materials from the bottom up in such a way that we enable things that otherwise would be absolutely impossible to do with traditional technologies, right? So in this particular talk, I'm going to focus on 4D printing and functionally graded materials, okay? So I'm going to start with 4D printing. 4D printing, started, actually, I think that the first example of 4D printing started at MIT about 10 years ago. And, 4D printing denotes additively manufactured structures that can change their form, property or function with time under stimuli, right? And this stimuli could be light, a change in the pH, temperature, magnetic field, stress, right? And 4D printing expands the potential of 3D printing by providing more degrees of freedom to engineering design, right? So this is an example. I think that this example came out of MIT. It's a polymer that was engineered in such a way that different elements of this polymer component responded differently to the the local chemical environment. I don't know if in this case it was a pH responsive material, but because different components were engineered with different sensitivity to the surrounding chemical environment, you could enable, for example, self-assembly or time-dependent actuation or motion in the part that they were making, okay? So this was in polymers. And actually to date, 4D printing has mostly exploited stimulus-responsive soft materials, right? So 4D printing is extremely advanced in the case of soft materials, and they have been used to demonstrate a number of applications that are important for a wide range of industries. And there are many types of soft stimulus-responsive materials, that have different mechanisms by which they actually respond over time under the presence of stimulus. But among all the soft, stimulus-responsive materials that are out there, chain memory polymers are some of the key enablers for 4D printing. And here I have a diagram from a recent review by Kwang in 2019, where they list a bunch of potential applications from biomedicine, tissue engineering, origami, and so on. They have different types of polymers, from single shape memory polymers, liquid crystal elastomers, composites, multi-material shape memory polymers, and so on. They also list all the type of different stimuli that can be used to activate this 4D, behavior, this time-responsive behavior. And this stimulus ranges from thermal energy, light, magnetic fields, changes in the chemical environment, the amount of water and so on. There are a bunch of technologies that can be used, from inject printing to other types of deposition techniques. And there's a whole ecosystem of applications, materials, and stimuli and technologies that have been used in the past to enable 4D printing. And if you think that this technology was first demonstrated about 10 years ago, the explosion in 4D printing in the case of soft materials has been extremely fast and exciting. Now the question here is, what about metals, right? So it turns out that shape memory polymers have a counterpart that is probably older than shape memory polymers in shape memory alloys. So these materials are metallic systems that are capable of undergoing a very large recoverable strain as a result of reversible martensitic transformations, right? So you have an austenite at low temperatures, for example, and as you increase temperature, there is an rapid military style transformation that takes this crystal structure and transforms it into a higher symmetry structure. And in shape memory alloys, this transformation, this martensitic transformation, is actually reversible and can be triggered by stress, temperature, magnetic field, or a combination of all these different types of stimulus, right? So shape memory alloys, they actually can undergo these reversible phase transformations. It turns out that shape memory alloys have some advantages relative to shape memory polymers in the sense that they can withstand, loads that are orders of magnitude the load of what a soft shape memory polymer can withstand. So you're talking about 200, 300, even higher, loads, while undergoing these reversible phase transitions. And they enable applications that are not possible with soft materials, right? So for example, if you want actuation at high temperatures, you're probably not going to be able to do it with shape memory polymers. And there are examples of shape memory alloys, including a lot of alloys discovered at Texas A&M by Professor Karaman, for example, that can undergo these reversible phase transformations at temperatures as high as 800 degrees Celsius, right? So clearly, as soon as you reach temperatures of 200 and above, having to carry loads that are hundreds of megapascals, these are things that, or these are operating conditions that soft shape memory polymers, cannot sustain, right? So there is clearly an opportunity to try to do something, related to 4D printing with shape memory alloys. Now, one interesting aspect of shape memory alloys is that they are extremely sensitive to minute changes in the chemistry and the microstructure, right? So here, for example, I have a plot for the transformation behavior, right? Basically the transformation temperature, at which temperature this reversible transformation is triggered for nickel titanium as a function of the amount of nickel. And if you look at this change, you can change the transformation temperature by almost 100 degrees Kelvin by changing the chemistry by just less than 1 atomic percent, right? More importantly, or, in addition to this, we have discovered in collaboration with Professor Karaman that if you subject some of these shape memory alloys to heat treatments, you can dramatically change the transformation behavior by controlling the microstructure of the material, right? So these materials are incredibly sensitive to chemistry and microstructure. So a key insight that we had in our group about, I don't know, like 4 years ago was that if we could locally change the chemistry and or microstructure of these materials, we could achieve location-specific behavior. And this could be enabled through the local control of the additive manufacturing process conditions. Okay, so the idea here is, if we know that these materials are highly sensitive to chemistry and microstructure, can we tailor the chemistry and microstructure of a material that has a uniform feedstock composition by just locally controlling the process conditions. So we're actually proposing here 4D plus printing, where we have, the 4D printing, the traditional 4D printing characteristics of being able to fabricate things that respond in time. But, the idea here is that we actually want to locally change the composition, so we control this actuation in time also in space, right? So the idea here is, can we actually print different locations of the part with different processing conditions? So every region of the part has different chemistry, and therefore we'll have different transformation behavior when we apply a particular type of stimulus, okay? This is a video that we have where, we printed a hand, at Texas A&M, and every single finger of the hand was printed with different process conditions. And as you can see, in this hand, different fingers are actuated at different times, right? This is not water, this is actually glycerin. It turns out that if we try to do this with water, we will see a lot of boiling and a lot of bubbles, so we wouldn't get a nice picture. So we basically had to figure out what type of liquid to use, and we settled on glycerin to try to visualize this actuation response with minimal visual disruption, right? And of course, this is an accelerated video. It turns out that the actuation, at least in this case, was not really fast. So this is not like a scary robotic hand. It's actually kind of slow. But here we are demonstrating that we can we could potentially control on a location by location basis the response of these materials, okay? So, essential elements to make 4D printing possible in the context of additive manufacturing is through composition control. So can we actually directly deposit feedstock that has, different chemistries? And there are 3D printing technologies, for example, that allow you to do multi-material printing. I'm going to talk about that in the second half of my talk. Or, in the case of a material that is like a shape memory alloy that is extremely sensitive to chemistry changes, could we actually exploit the fact that different elements in the alloy have very different vapor pressures to then enable the preferential evaporation of elements in such a way that we could locally control the chemistry? And of course, in addition to composition control, we could do microstructure control, and this could be enabled, for example, by controlling the thermal history of the material during fabrication. So the idea here, the key idea, is to change processing conditions as a function of location in the part. So, by the way, so basically we have demonstrated what is possible, but we haven't yet developed a whole framework that allow us to solve the inverse problem. It turns out that the inverse problem is very hard. We have just tinkered with the material and the process conditions to demonstrate that location specificity is possible in the context of 3D printing of shape memory alloys. But if you think about it, in order to enable this in an algorithmic way, you actually have to combine topology optimization, you have to model process and structure property relationships in additive manufacturing, you have to optimize the process, you have to validate and verify, and you have to make sure that your optimization is robust against changes in the local cooling conditions when you fabricate, right? So right now, I'm just going to talk about some steps that we have taken in this direction, but we don't have yet a complete story to tell. So on the process optimization side, what we have used is we have used a combination of physics-based models, machine learning, and experiments to try to come up with a framework that enable us to, find optimal regions in the processing space that lead to parts that have low porosity, right? So the first thing is, if you're trying to fabricate something, with additive manufacturing, the least you can do is to make sure that whatever you print doesn't have macroscopic porosity that would ultimately compromise the performance of the part, right? Pores lead to failure, such as fatigue, etc., right? So the first thing that we do is we say, well, we have this large processing space, we can change the power and the scan speed of the laser. can we detect what regions in the processing space lead to optimal, printing without defects? So the idea is we do some simulations, we compute some initial printability map, we do some single track experiments, we calibrate the models that we use to try to correct for, missing physics. We revise a printability map, and then, in the good region, the region where we do not expect to have these microscopic defects, we print bulk samples. And what we have found is that as long as we print things in regions that are, not, conducive to these microscopic defects, the properties that we get out of these materials tend to be very uniform, right? So, and that makes sense, right? We want the material to be not limited by the presence of microscopic defects such as porosity, right? And here we have an example of nickel titanium where, we have found the sweet spot using the framework that I presented in the previous slide. We have found that the sweet spot doesn't have porosity, and we have shown how we can fabricate these, bars of this material and that have, interesting and repeatable, stress strain responses. Now, the other thing, now that we find, how to print the material without defects, then the question is, can we actually use computational models to try to predict what is the effect of local thermal history on the chemistry and or microstructure of the material, right? So the idea is, can we build, physics-based models, right? And can we couple them with their experimental twins to try to build robust models that enable us the prediction of the change in chemistry as a function of changes in process conditions, okay? So we have one first step in this direction, and actually one student that was a lab mate of Kubra for a few years, Dr. Milad Ranayefar, he just defended his thesis a couple of weeks ago. He actually developed a modeling framework where he was able to connect a thermal model that was developed initially by Air Force Research Lab that was calibrated against experiments to a model that predicted the differential evaporation of nickel in nickel titanium shaped memory alloys. So we would basically predict how much nickel loss existed in a melt pool. Then, he built a multi-layer model that was able to integrate these single track predictions and took into account, the mixing of chemistries as you build successively these layers. And he was able to demonstrate that at the end, he had a computational framework that was in very good agreement with experiments, right? So here is just a prediction, a comparison of the experimental nickel loss measured by measuring the transformation temperature of these shape memory alloys with the computational predictions, and the agreement of 0.15 atomic percent in error is actually smaller than the resolution of chemical analytical techniques such as EDS or WDS, right? So we're able to build predictive models that are more precise than some, analytical techniques to measure the local composition of materials as they are printed, okay? After that, once we build this model, then we can build process maps that tell you how much the nickel content and the transformation temperature are going to change as a function of where you are in the power scan speed space, okay? And the idea is, sorry, I don't know what happened. The idea is once we, have this forward model, the idea is to start thinking about how do we invert these, forward models to try to start doing this closed loop objective-based algorithmic design for 4D printing, okay? So we are not quite there yet. I think we're starting to work on the inverse problem for 4D printing, but we don't have a lot of results yet. Milad has some preliminary work that is kind of exciting, but this is a very interdisciplinary project that requires a lot more people than the ones that we have right now. But I think that there's, some interesting future for 4D printing. it clearly has demonstrated, 4D printing has clearly been demonstrated as a very attractive area in the case of soft responsive materials. We think that, there's a lot of really cool stuff that can be done in the context of metallic, responsive materials, right? And this is an area that in my group, in collaboration with Professor Karaman and Elwani, we want to explore in the future, okay? So now I'm gonna switch gears and I'm gonna talk about another example of going beyond 3D printing, and this is functionally graded materials, okay? So, here what we are trying to do is to actually expand the design palette, right? So, compositionally graded alloys are promising materials, particularly because they allow you, or they enable new possibilities in part design, right? So imagine that instead of, doing topology optimization on a part to minimize, its total weight, imagine if you could actually print different properties in different locations of the part. So every location could be optimally designed for a particular performance characteristic. So for example, if you're 3D printing an turbine blade, maybe you want to make the surface of the blade oxidation resistant, but you want to maximize the creep strength or the strength at high temperatures in the core of the blade, right? Clearly, in some cases, you cannot have, an oxidation resistant alloy that is also creep resistant, that is ductile, that has high temperature properties and so on in the same monolithic material, right? Because if you actually want to do that, you probably have to over design and come up with alloys that are good at everything. And clearly that sometimes is not a attractive proposition. So the idea here is, can we enable more flexible designs by using the capabilities of 3D printing, particularly if we exploit multi-material printing to locally change the chemistry, microstructure, and properties of the part in order to locally and absolutely optimize the part performance for practical applications. So even though there is a possibility, there are gaps, right? So first of all, and I will talk a little bit more about it in the future slide, linear gradients are often infeasible, and I will explain why in a minute. And we don't have really design frameworks that take advantage of these capabilities in a systematic way, right? So our research objective is to create a computational methodology to design compositionally graded alloys with an arbitrary number of constituent elements that satisfy specific constraints and at the same time optimize design objectives, right? So, how do we do this in practice? There are many techniques for multi-material printing, but in our work, we have used directed energy deposition. So in this case, you print a material on a layer by layer basis, but what is different from additive manufacturing is that we're actually depositing the material and the power or energy at the same time, right? So we basically print by, shooting, a beam of powder and melting it on the fly and hoping that it sticks on the substrate so we can build a complex three-dimensional shape on a layer by layer basis. There are many possible engineering applications, and they, for example, can enable multi-material design. I will not touch this topic of multi-material design because I don't have enough time, but in principle, what compositionally graded alloys can enable is they can enable us the local optimal design of material compositions in different parts or regions of the part that we're trying to print. And then using the techniques that I'm going to show in a minute, we can then stitch together these multi-materials in such a way that they form a monolithic part. Unfortunately, when you try to do this compositionally grading with linear gradients that just connect one start composition to a net composition, it turns out that variable phases appear, and oftentimes linear gradients lead to undesirable properties that can compromise the manufacturing of the part and diminish their performance. So it turns out that computationally graded alloys are challenging to print. So there are many examples in the literature where people have actually tried to print linear gradients from all kinds of base alloys, from steel to Inconel, from steel to titanium 6-4, and so on. And it turns out that 90% of the times, these linear paths fail because you form brittle faces that end up compromising the mechanical integrity of the part. They can also, if you do a linear path, you could also create property discontinuities, for example, thermal expansion coefficient, that would compromise the mechanical performance of the part because you can generate internal stresses or other types of undesirable conditions inside the part that would actually compromise its performance. So, there have been some attempts to use, computational tools to design these alloys. So most of the times what people have done is to try to print or predict ternary phase diagrams and then actually find by, human intuition, a path that may actually run around obstacles. But the problem is that when people use these approaches, they are extremely difficult to scale and very difficult to deploy in the case of multi-component materials, right? Why? Because humans are not built to be, to see things in more than 3 dimensions. So when you have many more dimensions in your design problem, it is extremely difficult to come up with robust composition paths. So what we have done in our group in collaboration with Professor Malak is to look at the gradient design problem as that of motion planning. So we're actually trying to say, well, can we formulate the design of a gradient alloy as a path planning problem? Now, there are, for decades, a lot of engineers in a lot of fields have tried to develop algorithms that actually enable the design or the plan of a path. And these type of techniques have been used in many types of problems, from protein folding to, mapping of, trajectory in autonomous vehicles and so on, right? So the question that we have is, could we actually leverage these path planning technologies and transform them in such a way that we can use gradient compositional design in an algorithmic way? So basically what we do is we're trying to minimize a particular function, and this function could be a property, or it could be the length of the path or some other quantity, subject to the fact that you start and end at a particular point in the chemical space, and subject to constraints related to the fact that you want to avoid regions in the chemical space that are undesirable, maybe because there are some phases that may form that are undesirable, or maybe because there are some regions in the chemical space that have a low melting point or some other undesirable characteristic, right? So can we actually map a trajectory in an n-dimensional space, right? Maximizing or minimizing a quantity while avoiding obstacles. So this is the methodology. We use computational tools, computational thermodynamic tools, to actually map the obstacle space. Then we use machine learning methods to try to classify the regions in the space that are unfeasible, right? With these classifiers, we build an obstacle model, and then we present this obstacle model to a path planning algorithm, such as RRT-FN, that enable us the connection of points in chemical space in such a way that we avoid obstacles, and at the same time, we minimize or maximize a particular, property, right? And of course, in addition to, the phase characteristics, if we have a property model, we could actually build arbitrarily complex cost functions that can be built into the, path planning algorithm in order to obtain, some measure of optimality in the gradient that we're fabricating. So we have some experimental results. This is an example, that was published, a few years ago, where we tried a naive linear path between a particular alloy and stainless steel, right? And of course, what we found when we tried this path is that the sigma phase, which is really bad in steel alloys, is prevalent for much of the path. And then what happens when you try to print this naive path, you actually have cracks because you have the formation of these very brittle phases. On the other hand, when we plan the path, this is an early example. Now we're way better, and we can actually match almost perfectly the planned trajectory. But this was one of the earliest examples. We design a path, and then we try to approximate it with our multi-material printer. We were able to see a compositionally graded path that had no cracking, and we didn't observe any sigma phase even after heat treatment under temperature conditions where the sigma phase would be observed if you actually had a composition in this region where you have sigma phase. Now, so we have demonstrated that we're able to actually optimize a path by avoiding obstacles. But what about functionally grading, right? So what we have presented is just compositionally grading, but functionally grading is about grading not the composition, but actually a property or a function, right? So, and this has many applications. For example, largest continuities in the thermal expansion coefficient could lead to significant stress concentrations, right? So a property profile that is smooth may actually minimize these changes, and therefore, the stresses that are built up when the material is subject to temperature changes. And that is just one example. We could actually grade on purpose other types of properties, such as strength, or elastic modulus, or other types of properties for different applications. Okay, so what we know is that it is unlikely to find these linear property profiles between arbitrary compositions. However, one thing that my former student Tanner Keir discovered was that if we ensure that the path in the composition space was monotonic in the property space, that is, if we ensure that the trajectory changed the properties only in one direction, so it always went down or up, we could then create any arbitrary linear or nonlinear profile of this property by just controlling the deposition rate. So the idea here is we actually have to find a path that is monotonic. And then once we find the path that is monotonic, then we can write any arbitrary property profile as long as it's bounded by the limits in the property that we have between our start and our end goal for the composition trajectory, right? So to make any gradient part with optimal properties, with arbitrary property profiles, the only thing that we need is to find a gradient path that has this monotonicity behavior. Okay, so this is an example. We looked at the iron, cobalt, chromium system, and we actually tried to map to a path that connected two different compositions. And we found an optimization problem where we tried to minimize the length in this trajectory while ensuring that we didn't have a particular phase, that we avoid obstacles, and at the same time we tried to make sure that the path was monotonic in thermal expansion coefficient. So this is this is basically an example when we actually do the path planning with the shortest path. We may be able to avoid the sigma phase, but unfortunately the thermal expansion coefficient actually changes in a non-monotonic way as a function of composition, right? When we apply the the path planning and we actually enforce the monotonicity constraint, what we find is that the algorithm is actually able to find a more complex and longer path, but in this case the property is monotonic. And if it's monotonic, that means that just by controlling the deposition rate, we can print any property profile that we may see fit. Okay, this is just an example between the monotonic and non-monotonic path, and clearly this path is likely to have less problems with thermal expansion stress buildup than the non-monotonic case. Okay, So future work in this context of functionally grading, we have done compositionally grading, but if we're trying to print this, we actually have to map the processing space in such a way that we minimize the formation of these microscopic defects. So the idea is to combine composition path planning with process path planning in such a way that we obtain not only optimal chemistries, but also optimal processing conditions in every material point in such a way that we minimize not only, we optimize a particular property while avoiding these, undesirable obstacles, while at the same time ensuring that the composition path is printable. And of course, the other thing that we want to do is to integrate this with part design. So can we actually, exploit technologies such as multi-material topology optimization in such a way that we can locally optimize the chemistry and properties of the part as we 3D print it, right? And this is one of the future ideas that we have for this research program. Okay. Now to conclude, I'm a bit longer than I expected. 3D printing is on the cusp of transforming entire industries. As we have seen in this talk, the major advantages are flexibility in design, mass customization, more efficient utilization of materials. But we believe that even more transformative technologies could be achieved by going beyond 3D printing, exploring the potential of additive manufacturing to locally tailor chemistry, microstructure, property, and function. And with that, I would like to thank you for your attention, and I will be happy to entertain questions that you may have. Thank you.
Thank you, Professor Arroyave, for the great talk. We have some time for questions, and we have the first question followed from Yozu. Please go ahead.
Oh, hi. Thank you, Professor, for this wonderful talk. It is very inspiring. I'm Yao, and I worked with Professor Mishra and Professor Nara Sneha in wire arc additive manufacturing. And what we are doing is now play with the thermal history to realize microstructure control, and then we can tailor in the mechanical properties. I noticed that you also mentioned that it is one possibility, one task in your groups. But what I want to say is that prior to this wire arc additive manufacturing project, we, Professor Nara and I have spent 2 years working on metals 4D printing, which is super interesting project. What we are what we have looked in is both nitinol and the magnetic shape memory alloys, nickel, manganese, gallium. And as you mentioned, your work in nitinol composition controlling for different properties is one of the source of the inspiring to us. And our idea of using 3D laser powder bed fusion techniques to realize 4D printing is a little bit different. We wanted to use material science technical tools to understand what microstructure do we want. For example, for nickel, manganese, gallium, from the calculation, what we are aiming to is to realize large columnar grains with high texture, which is challenging for additive manufacturing to fabricate. So, so my specific question is that, do you find any texture or microstructure requirements for nitinol in both DED or laser powder bed fusion process to realize a 4D printing, 4D metal printing in your project, in your group? Thank you.
So that's a very good question, Yao, and yes, you're also doing really interesting work. So we haven't exploited texture control that much, but we have noticed that there is a preferential texture in nickel titanium, right? Depending on the cooling conditions, you could actually, enable textures that are oriented along specific crystallographic directions because probably they are the most mobile, solid liquid interfaces, right? So There is some measure of deterministic texture selection based on the process conditions. We haven't explored that yet, but potentially this is something that can be engineered and controlled, right? Right now, for example, people are doing investigations with using, shaping of the laser beam, to have different shapes in addition to just having a spherical shape or cylindrical shape or circular shape. People are also playing with multi-laser printing. So you could use one laser for melting, and then you could use locally another laser, for example, to engineer the thermal gradients in such a way that you control the growth of a particular crystal in a particular direction. So I think that we're just scratching the surface, right? Additive manufacturing is evolving super fast, and there are many different potential technologies to locally change the solidification texture of alloys, in addition to changing the chemistry and other features of the material. So we haven't explored that yet, but it's possible to do.
Okay, thank you, Professor. And for 1900, what we observe is that the phase transformation is controlled by thermal, so different topological optimization for the final parts may affect the heat transfer, like in real time heat transfer, which can control the deformation as well. That's interesting part. And Professor Nara, I think, will still working on 1900 in CMU. So I think there is a lot of opportunities for exploring these materials and collaboration.
I agree.
Thank you.
Thank you.
Thank you, Professor.
Is there another question? I don't see any questions.
Maybe I went too fast or so. I don't know.
So Ray, I don't have questions. So very excellent work. So this is very inspiring. I'm really impressed, like the research you are doing, especially how to combine this traditional our modeling approach, combined with the machine learning, especially. I am really inspiring your work that you have borrowed the concept like this autonomous driving and then trying to find a path. So that is really impressive in the material design. I think this is, I would say this is a breakthrough, at least, for the mind. Yeah. So congratulations on your excellent work. Yeah.
Thank you, Yusong. And actually, this is, to all the students, right? I want to say this. To all the students, this is an example of the cool stuff that can happen when different people with different backgrounds and different training get together and start talking. So this idea started, over a beer, with, I was having a beer with Rich Malak, who is a colleague of mine and a good friend. And we were just talking about, we were just like riffing ideas and, throwing ideas at each other. And then suddenly I brought this idea that I had of, doing, design in a compositional space and so on. And he said, oh, this looks like a path planning problem, right? So why don't we let's try to explore this idea. And by the way, now we are moving beyond this. So now we're actually trying to do road mapping. So instead of planning, 2 points, like the connection between 2 points, we're trying to use the approach that Google Maps and Apple Maps, etc., use. And we're actually trying to figure out how every point in an alloy space is connected to every other point, avoiding obstacles, right? So imagine that you have a street system, and we're actually trying to say, well, if I want to go to this address and this address, can I actually map all the ways in which these two addresses are connected, right? First, so we have a roadmap of the material space, and then we can do, and this is something that I didn't talk about, we can do multi-material design where we say, well, I like this. I'm going to try to find the best coffee place in town. And right after coffee, I want to have the best pastry, right? Mm-hmm. I'm going to optimize my enjoyment by actually trying to find the fastest route or the fastest trajectory between the best coffee place and the best pastry place in town, right? And I build this map and I figure out how to connect it. Now, I could change my preference and I would say, you know what, instead of pastry, I want to have ice cream, right? If I have a roadmap, it's very easy to just reroute my trajectory and just find another, optimal trajectory that takes me from a coffee place to a like an ice cream place that is the best, right? So we haven't developed the idea yet. Our student is working on a paper that's kind of promising, going in that direction. But this is what we want to do. We want to do basically a roadmap of the material space where every feasible alloy is connected while avoiding obstacles and optimizing other properties at the same time, right? So this is future work. It's not funded yet, but we are excited. I think this is a cool idea, and we're trying to pursue it in the future.
Mm-hmm. That is great. So one last question. So is the paper published regarding this machine learning work you showed?
So the path planning papers are published already. Mm-hmm. I mean, I can send you some papers, and the 4D printing papers, we just published the first forward model where we connected thermal histories to composition change. Mm-hmm. And we have another paper where we did uncertainty analysis of the forward models to try to figure out whether we could do robust design. That's another message to the students, right? If you're doing computational or experimental work, you have to be aware of uncertainty in your experiments and your simulations, right? If you treat your experiments or simulations as perfect without error bars, you cannot really do design, right? If you're trying to do design, you have to be aware of the uncertainty in your design space in order to make sure that whatever you design is robust against minute changes in the design conditions that happen, by necessity, right? So if I may give 2 lessons, don't be afraid of being interdisciplinary. Talk to people that are outside your field. Be aware of uncertainty if you're actually trying to do design.
Yeah, okay. Yeah, very nice. Yeah, thank you very much, Ray. Yeah, okay. Good work. Thank you.
Very interesting. Thank you. Yeah, I'm pleased to say that I think most people got the point of the 4D printing so in a little poll. So really appreciate it. It's funny. I've tended to think of you as more ICME, but this is really, really nice. I
get bored, so I don't want to do the same thing over and over again, because so that is another message, right? This is not a job. It's like a hobby of mine, being a professor, because I get to try different ideas that my brilliant students like Kubra, execute. So I get bored very quickly, and I don't want to do the same research for my entire career, because otherwise then what's the point, right? Life is too short. And I tell my students, this is like being a musician. Imagine that you're a musician, like you're the Beatles, and you only play your greatest hits and that's it, right? Or, Rolling Stones or U2. You don't want to play, even though, U2 has some classic songs from the 80s, they still write new songs, right? Why? Not only because they want to sell more records, they sell plenty of records, but because they get bored otherwise, right? So you have to try new things, in your life, in your job, your profession, so you don't get bored, because the more interesting your job is, it becomes less of a job and more like a hobby or a thing that you do just to have fun.
Terrific. Great. Well, thank you very much once again. I really, really appreciate it. It's great to see you, and some really nice work you're doing. So thanks.
May I ask one?
Thank you, Kubra, and thank you to everyone for your attention.
We don't have a follow-on meeting, so if there's some more questions, you're welcome to continue.
Yes, I don't have much. This is our spring break.
Okay.
So that means that all my meetings were canceled and I don't have classes. So if anyone has other questions, I will be more than happy to answer them.
Wonderful. I'm going to turn over the hosting to Kubra, and then can have Matt's question. Okay. Right. Thank you.
Yes, please go ahead. I heard there was a question. I don't know who was asking for.
Sorry, yeah, I did have one quick question, please. Thank you for the talk, Professor. So in my work with AM materials, one thing I've noticed that could potentially tie into your roadmap models is you're specifically trying to avoid kind of critical compositions where you're getting, for instance, sigma phase. One thing in AM materials, as I'm sure you've also noticed, is you get microsegregation where you get cellular substructures. Do you kind of build in that a buffer zone within your roadmap such that you're avoiding those compositions that you can get with microsegregation?
That is an excellent question. The answer is not yet, but we have, we have in a separate project, we're actually trying to design alloys, and the tendency towards microsegregation is part of what we're looking at. And actually, Kubra's work got us started in that. So Kubra built phase field models in additive manufacturing, and she was able to predict segregation in the interdendritic regions under different process conditions. So we are building fast-acting models to predict the tendency for segregation in this, and of course, segregation is a function of chemistry and phase diagrams, but also processing conditions, right? So if you have a very large, if you have an alloy that has a very large solidification range, it's probably going to be more prone to segregation, but you probably can find process conditions that lead to partitionless solidification, right? Now, the question is, and remember that I showed this processing map, at the beginning. The question is, for example, let me just go to the process maps. If let's say that this is the optimal region in the processing space that leads to defect-free components, right? Maybe, for this alloy, you have a large solidification range. Maybe it turns out that for most of this feasible region, you have segregation, right? Why? Because the solidification range is like 100 Kelvin or something like that. And there's not going to be a process condition, in this feasible region that is going to take you to a point where you have partitionless growth, right? Then that may be a limiting factor, right? Maybe the segregation behavior is only observed at scan speeds below 0.5 meters per second, right? So if you know that your segregation tends to form in this range, maybe you want to constrain your printing in regions that escape this segregation behavior, right? So that's a very good question. We have right now in a different project a way to predict this tendency towards segregation. But we haven't incorporated it yet in the road mapping idea. Actually, the road mapping idea is just an idea. We haven't even written a single paper. My student is working on the first paper where he demonstrates this, idea, but we haven't done much yet. Okay, but yes, you're right. We could also, for example, find compositions that are less prone to hot cracking, right? Or other types of detrimental behavior.
That's an excellent answer to my question. Thank you. And then I suppose one more thing that ties in with your answer in terms of tailoring the processing conditions. I've done a bunch of work on optimization of AM processing conditions, and one thing that we're also noticing will come kind of in tandem with changing processing conditions is kind of obviously, as you've noted, when you change your cooling rate, you're going to get a different substructure size, and that'll also give you the ability to tailor mechanical properties in that way too. So it's kind of an interesting multivariable problem where changing your solidification rate will give you a difference in microsegregation, but also give you a difference in the localized strength of the material too. Yes. So it'll be wonderful for the whole community if you're able to figure this out for us.
So we have some ideas on how to do it. Actually, a student of mine is working on a fast-acting thermal model that is better than the traditional thermal models that people use, where you make a lot of assumptions about the geometry of the space and so on. So this model is very fast, in milliseconds in a GPU computer. And it is a combination of an analytical solution to the heat transfer problem with a numerical solution. And we can So he can simulate, for example, like imagine that you have a part that has this particular shape, right? So he can simulate the thermal histories in different locations of the part, including corners, right? That have different cooling conditions. So we could potentially, for a part, we could then, locally find what is the optimal region for printing, given the different local cooling conditions that you have as you build the part, right? So again, we haven't published a paper yet on this, but we have some ideas on how to tackle this problem. So we build these printable maps on a geometrically aware basis.
That's fantastic. I wish you luck with that work for sure.
Thank you.
We have another question.
Sure.
Okay, if not, I think we can now end the seminar session.
Well, thank you, Kubra and Adam and everyone for inviting me, at least virtually. I wish that I was there, but I just couldn't make it happen. Thank you to the students for your attention. And if you have any further questions, you can find me easily. There are not many Raymundo Arroyaves, right? I think that my father is in Mexico and he's a retired doctor. My kid is in 7th grade, so he has not written a paper yet. So I'm the only one that writes papers in material science. So you can find me very easily. And if you have questions about my talk, I will be more than happy to answer them. Okay. Thank you all and have a nice rest of the week.
Thanks so much.
And I have actually one really quick more thing, Professor.
Sure.
As a heads up, when looking at those little density cube builds that you showed, I noticed that you seem to have them oriented such that the recorder blade's gonna hit parallel to some of the long faces of the specimens. If you rotate them a couple of degrees, it'll make it so you could potentially have less issues in terms of porosity, because the recorder blade, instead of hitting a whole lot of solid edges at the same time, because the material tends to kind of the edge. Yeah, rotate them a couple degrees.
Yeah, so thank you for that, Matt. I will let so I don't do the printing. So my colleague Ala Elwani has the printers. But yes, I will discuss that with him. Thank you for the advice. I will pass it on.
Sure. Good luck.
Thanks.
Okay. Thank you again. So we are gonna just end this seminar session. Thank you.
Thank you, Kubra. Thank you all. See you later. Bye-bye.
Very nice to see you.